Joining us today. We will be starting just a couple of minutes late, but we will be starting momentarily. So just to give you all a few minutes warning. Thanks. Don't go anywhere. Okay. I think we might be ready to go. Thank you so much, all of you, for your patience while we're sorting out some technical difficulties. My name is Rachel. I'm a researcher at Woodwell Climate Research Centre, and I'm really happy to welcome you to the Cryosphere Pavilion today here in Glasgow. And we have an event now looking at Antarctica and the Paris Agreement goals. And of course, I'd also like to welcome all of you joining virtually. So those of you joining from the Cryosphere Pavilion hubs in Stockholm and in Geneva, and of course, all of you tuning into the live stream as well. And please do feel free to drop those questions that you have throughout the event into the chat as we go along. And we're really lucky to be joined today by Rob DeConto, who is co-director of the School of Earth and Sustainability. And without further ado, I think I will hand it over to Rob for our first presentation. Thank you.
We apologize for the technical difficulties. Maybe it built some suspense. So, I thought because we're here in Glasgow, it'd be nice to reflect on Paris and the aspirations of the Paris Climate Agreement and what the implications of that agreement are for the Antarctic ice sheet, and why we'll be talking about Antarctica today. I know there were some presentations this morning about Greenland. Is that Antarctica is still really the wild card in future sea level rise, and it is a difficult ice sheet to model, to predict what it's going to do in the future, and so there's a lot of uncertainty around its future fate in a warming climate. But I think what you're going to see next is some of the recent research is suggesting that exceeding the Paris aspirations of 1.5 or plus 2 degrees, we're going to be starting to flirt with disaster. So just a quick little bit of context. So this curve here on the right is it's the record of sea level rise. Sea level has been rising. We've been measuring its rise for several centuries in some places using tide gauges all over the world. Today, the rise of sea level is on the order of almost 4 millimeters per year. And that doesn't sound like a lot, but year after year goes by and it's accumulating, and there are growing impacts around the world because of that steady rise in sea level. Actually, it's not a steady rise in sea level. And you can all, I think, see this at the end of the record in the 2000s and onward. There's a little bit of a bend. You can see that orange curve sort of looks like a banana a little bit. The pace of sea level rise is accelerating. And the acceleration is coming from increasing contributions of land ice. Mountain glaciers, the Greenland ice sheet, and the Antarctic ice sheet are beginning to lose ice, and that water is going into the ocean and contributing to rising sea levels. In the 20th century and earlier, the dominant contributor to sea level rise was really thermal expansion of the oceans. The oceans have been absorbing about 90% of the extra heat that we're putting into the system with greenhouse emissions, and that warming ocean is causing a rise in sea level because a warm ocean takes up more space, lower density water. But there's been a real fundamental change in the Earth system, and this will be a little clearer. There's been a fundamental step change in the Earth system, and that change is that thermal expansion of the oceans is not the dominant driver of sea level rise. It's land ice melting, the contribution of water from glaciers, Greenland, and the Antarctic ice sheet. So we'll come back to this notion of, okay, today, 4 millimeters per year, acceleration. We're having a hard time in many places coping with 4 millimeters per year. And so I think the rates of potential sea level rise we'll be talking about in a few minutes should be pretty eye-opening. Okay, this is a really important, clear message. This is a colleague, an American geologist. Her name's Andrea Dutton. She's a professor at the University of Wisconsin. And Andrea is standing here on the left. You can see some big granite blocks. She's in the Seychelles. She's standing on a piece of coral, a coral reef. And Andrea's dated that coral, and she knows it's about 128,000 years old. This was a time in Earth's history that the geologists call the last interglacial. We live in an interglacial. We don't live in an ice age today. The previous interglacial, before the last ice age, is the last interglacial, 126,000 years ago. To a geologist, that's yesterday. That's not a long time in the past to a geologist. And that reef is 8 meters above present-day sea level. And here is another example. This coral dates the same age as the one in the Seychelles. It's in Florida, 8 meters above sea level. So we know that the ice sheets are sensitive to a little bit of warming because the climate 128,000 years ago was actually very, very similar to today. So even with a climate state like today's, let alone something much warmer, you give the ice sheets enough time and they're going to respond and they're going to contribute to sea level rise, and quite a bit. The world with 8 meters more sea level than today completely remaps our global coastlines. Okay, now the two big ice sheets, Greenland and Antarctica, where most of the potential sea level rise sits. Here we see Antarctica on the top, Greenland on the bottom. The graph on the left is showing the loss of mass of those two ice sheets. So if the ice sheets were healthy and happy and in equilibrium, so that the snow falling on the interior of the ice sheet equaled the amount of melt and the amount of calving where the ice is actually reaching the ocean, if what's going in through snow were to equal what was going out, the ice sheet would be stable, equilibrated, and the red and the blue line would be flat along the top. They would be staying at zero. So you can see that they're not in equilibrium. They are losing mass. And again, I think you can all sort of squint a little bit and see that there's, again, this banana shape to those curves. So the rate that they're losing mass, there's an acceleration. Okay, today, Greenland, the blue curve, you can see it's losing ice faster than Antarctica. Okay, but, and this is the big but, is that Antarctica, the ice sheet on the top, that today is losing ice slower than Greenland, has 8 times the potential to drive sea level rise than Greenland. So, okay, today Greenland is the dominant contributor, but if that were to change, then there's potentially an enormous amount of sea level potential locked up in that ice sheet. I like to show this slide. I have to remind myself, even though I work there, I've stood on the ice sheet, I model it, I study it. It's really hard to get your head around the scale of the system. It's enormous. 57 meters of potential sea level rise in that ice sheet. Okay, now this is a really important point that will come up at the end of the presentation today. Sea level rise around the world is not going to be felt the same for everyone. And the reason why is that when an ice sheet like on Greenland or in Antarctica begins to lose mass, and that ice now becomes meltwater and the water gets distributed throughout the world's oceans, we start to change the Earth's gravitational field. And even the Earth's axis of rotation changes a little bit when we start to have a redistribution of mass. And even the solid Earth itself isn't so solid, and it responds. So these are the so-called fingerprints of what sea level looks like if ice loss happens on Greenland versus Antarctica. And this is worth actually paying attention to. So this line between the red and the blues in the orange, if you follow that line, that is a place in the ocean where sea level change happens by the amount that you expect given, let's say, a 1 meter worth loss of ice on Greenland. And we look at the Greenland map, and this part of the world feels about 1 meter of sea level rise. Okay, all the blue colors and the greens and even into the yellows, they feel less than a meter of sea level rise. And the reason is that as Greenland is losing mass, it's no longer sort of pulling gravitationally on the ocean around it. And so Greenland is no longer attracting the ocean around the Greenland ice sheet very much. And that loss of gravitational pull means that the waters right around Greenland don't rise as much as you would expect. Okay, but that means that if there's a meter of worth of sea level rise contributed by a loss of ice on Greenland, and the waters around Greenland don't rise by a meter, that means that someplace else has to compensate. So when you look far away from Greenland in the red colors, those parts of the world actually feel more sea level rise than the 1 meter's worth of ice loss that went into the world's oceans. And if we looked at Antarctica, in particular, the same type of map for a loss of, let's say, 1 meter's worth of ice from the western part of the Antarctic ice sheet, you can see the map looks completely different. It's flipped upside down. Close to West Antarctica, you see less than a meter of sea level rise. In fact, if you go right up close to the ice sheet, even though an ice sheet is losing mass and contributing to global average sea level rise, right up next to the ice sheet, sea level is actually going down. So if we look at the Greenland example, this is really nice and appropriate because we're here in Scotland. You can see the 0 line in those dark blues basically runs right through the UK. That means that if the whole Greenland ice sheet were to go into the ocean and cause 7.5 meters of sea level rise, the UK would feel very little change in sea level. But far away from Greenland, down here in South America, they would be feeling more sea level rise, maybe 130% or 1.3 meters, even though the global average is 1 meter. So I hope that was clear. So you can see that there are going to be big losers and big winners in terms of impacts from sea level rise, depending on whether it's Greenland that's the dominant future contributor or the Antarctic ice sheet. For the Northern Hemisphere, we have up here a lot more to worry about in these dark red colors in the Northern Hemisphere. And you can see, I know some of my European colleagues like to call the bullseye around North America sort of a karma effect, in that you can see the impacts are going to be really bad, let's say in New York, in Boston, on the east coast of the US, in the Gulf of Mexico, if Antarctica ends up being the dominant contributor someday to future sea level rise. Okay, and that point will come up at the very end, again, when we talk a little bit about the climate justice implications for Greenland versus Antarctica. Okay, now, Antarctica is much bigger. It's responding slower today, but it's a fundamentally different system than the Greenland ice sheet because of these maps here on the left. This is what a map of Greenland on the top and Antarctica on the bottom look like if we take the ice sheet away and we peer down onto the bedrock. The green parts are land that is above sea level, and the blue parts are land that are below sea level. So a lot of the ice sheet itself in Antarctica is actually sitting on bedrock in many places that is way below sea level. So you can see, for example, a lot of the West Antarctic ice sheet here is sitting on blue and dark blue. It's sitting in a bowl-shaped basin that in some places is over 2 kilometers below sea level. So the fringes of Greenland are mostly pulled back a little bit from the ocean, and there are thin fingers of outlet glaciers that are flowing out of the ice sheet into the ocean. Antarctica is different. The ice sheet itself, vast stretches of it, are actually right up against the ocean, interacting with the ocean and feeling a warming ocean around its edges. So Greenland's ice loss today is really mainly being driven by a slightly bigger fraction of the total ice loss on Greenland is being driven by just simple surface melt. The air temperatures are getting really warm in the summer, and they're driving huge rivers of runoff. Some of that water actually refreezes within the ice sheet during the following winter, but some of it, as we know, is making its way to the ocean to cause some additional sea level rise. Antarctica's main contribution to the ocean is to ocean sea level rise is happening through dynamic processes. The ice sheet is beginning to flow faster out into the ocean in certain places because it's still cold enough, just cold enough in the summertime around most of the Antarctic margin, the edges, so that we're not seeing a lot of melt on the surface of the ice sheet. It's ocean warming today that is really the dominant driver of the response of the Antarctic ice sheet. Now, the question is, will the world get warm enough so that Antarctica will start to look like Greenland, in that the temperatures in the summertime start to get warm around the edges of the continent that are more equatorward, so that in the summertime we start to get surface melt. And in that case, Antarctica would be being attacked really in two ways. One, interaction around the edges and on the underside of the ice sheet by the ocean, and potentially from warming on the Earth, on the ice sheet surface. Okay, this is a cross section of an Antarctic outlet glacier. And the flow in this diagram, so we can see ocean out here to the right, the ice sheet is to the left. The ice sheet is flowing under its own weight from left to right. So we have snowfall on top of the ice sheet here on the left. Snow comes down, accumulates, and then the ice flows from left to right out into the ocean. Now, this is a nice diagram because it's showing us, it's one of these examples of a stretch of the Antarctic ice sheet that is interacting directly with the ocean. Now, once the ice sheet starts to thin enough where it's reaching the ocean, this point right here, we call that the grounding line. So that's the point where the ice sheet is no longer sitting firmly on the bedrock. It's actually lifted now off of the bedrock and it's mostly floating. So you can see there's a big long extension of this stretch of the ice sheet poking out into the ocean, and we call that an ice shelf. And these ice shelves that provide sort of an apron around a lot of the Antarctic continent. You see this long extension of the floating ice sheet where big icebergs, we read about these big icebergs breaking off of these ice shelves every once in a while. They are the key to Antarctica's future. They are the key to Antarctica's future because where these ice shelves touch down on features on the seafloor, and I tried to draw a little cartoon of that here, like these sort of seamounts poking up into the bottom of the ice shelf. The ice shelf is flowing from left to right. And now you can see it's bumping into something. So there's some resistance to the flow of the ice shelf. And that resistance is translated back up into the ice sheet. So the ice shelf is providing some resistance. It's sort of holding back the flow of the ice sheet from the continent out into the ocean. And we call that a buttressing effect. So in places where we're seeing the ice shelves thin or break up completely, the buttressing, the resistance to the flow of the thick ice upstream speeds up. And we've actually, it was a theoretical idea decades ago. Then we actually observed it happen. And now we're able to model those sorts of processes in the models that we're using to make predictions about what the ice sheet is going to do in the future. So if we lose these ice shelves around Antarctica, we allow the ice sheet to start to flow faster into the ocean. So there's the buttressing represented by the red arrow, trying to slow things down, right? And you can think it's very intuitive, right? We're just holding up the edge of that ice sheet. Okay, so a number of different modeling groups around the world, including mine, have been developing models, numerical models, computer models that run on supercomputers to simulate all these processes, the flow of the ice shelves, the buttressing. And then we even simulate the climate above the ice sheet, changes in the temperature that make meltwater, for example. And we try to simulate the temperatures in the evolution of the ocean underneath and around these ice shelves. Okay. There has been one really important missing mechanism that our community hasn't really been, I think it's been underappreciated and it isn't represented in a lot of the models. And it's this is an example. So this is one of these floating ice shelves we were just talking about, the Larsen B ice shelf. This is a satellite image of it. It's about the size, it's hard to get against the scale of the Antarctic system. It's about the size of like a New England state, like maybe the state of Connecticut. It's about 600 or 700 meters thick, where the ice is flowing out of these glaciers out into the ocean to become an ice shelf. So you can see those glaciers, they're flowing out into the ocean and they are coalescing into this ice shelf. Now in this satellite image, you can see some dark spots. So those dark spots are water when this satellite image was taken. So it had been a really warm Antarctic summer that year, and meltwater, liquid water, was starting to pond and to flow into crevasses on the ice shelf. And an extraordinary thing happened shortly thereafter. It broke up. So the meltwater was getting into crevasses and wedging its way down through the ice shelf. It was moving and making the ice shelf flex, putting additional stresses onto the ice shelf, and it wasn't able to hold itself together. It broke up. And what happened was the glaciers that were flowing into the ice shelf no longer had that resistance, that buttressing, and they sped up by a factor of 3, others even faster. Okay, now this didn't cause catastrophic sea level rise because these glaciers that were flowing into this particular ice shelf didn't have a lot of ice to contribute to the global ocean, but other glaciers in Antarctica do. Okay, this is a nice close-up image of this big outlet glacier that was flowing into that resisting, nice, healthy ice shelf. After the ice shelf broke up, the edge of the glacier started to flow fast, but it also started to back up into its fjord. So it was flowing faster because there was no resistance, but it was still able to back up into the interior of the ice sheet itself. The reason why was it wasn't just about the fast flow. It was also about calving, the breaking off at the edges of this glacier. And the breaking, the brittle failure, the mechanical fracturing of the ice was actually outpacing the fast flow out toward the sea, allowing the glacier to actually back up into its fjord. Now, these two processes, this one, like what happens to big ice shelves when they get covered with meltwater, and then accounting for the breaking of the ice sheet itself back into a deep basin, are mechanisms that we hadn't been including in models that we've been using for projections of the future. Okay, so there's only been one continental scale ice sheet model that has attempted to incorporate these processes. We've seen them, we've witnessed them, they are observed, and yet they've largely been ignored by the modeling community. So my group took a stab at incorporating these processes. And what it did was it shows, and this is the bottom line, that when Antarctica gets warm enough so that in the summertime, we start to have temperatures rising above freezing, we start to get meltwater on these ice shelves, they break up. And when they break up, really all hell breaks loose because the ice starts to flow faster and it starts to break up in some places at the same time. Okay, here are two examples of two really impressive, beautiful outlet glaciers in Greenland where this process is actually happening. The Helheim Glacier here in southeast Greenland, and in western Greenland, the Jakobshavn Glacier. You can see these are glaciers that have lost their buttressing ice shelves. They are breaking off at their edges. They are flowing very fast out toward the ocean and also backing up into the interior of the ice sheet and contributing to sea level rise. So we have observational evidence that these sorts of mechanisms are happening in Greenland today, but if they start to happen in Antarctica, what happens? Much bigger system. So we build models, we try to incorporate these physics, and then we have to test the physics. Is this something that we are able to replicate, for example, past events? And one of the important tools that we use to test these models that we use to predict the future is we see if the models are able to replicate events in the geologic past. So remember the corals 8 meters above sea level that we talked about at the beginning? Well, right, we want to make sure that the models can replicate those sorts of past sea level changes. If they can't, then maybe they're either not sensitive enough or they're missing some physics that we haven't thought about yet. If they simulate much more than 8 meters, for example, of sea level rise during the last interglacial, then we know that the models are probably too sensitive and we have messed something up and we go back to the drawing board. So we use modern observations. Antarctica is losing ice today. We make sure that the model can replicate today's system. And then we look to the geologic past to also see if we can replicate past changes in the ice sheet. And when we're satisfied that we can A, simulate the modern system, and B, simulate examples of the past, then we feel some comfort and confidence that we can say something about what's going to happen in the future. Okay, now this is an example of high emissions, a high emissions scenario, the so-called RCP, so not the SSPs, but the RCP 8.5. This is a pretty extreme future emissions scenario, 4 degrees plus of global warming by the end of the century. And you can see here on the bottom of these graphs, it's years going from the year 2000 out to 2100. Okay, now the black line represents our best estimate based on hundreds of simulations of a model that incorporates these new processes. And the blue are incremental confidence intervals going away from the black line, the central estimate, between 5 and 99. It's actually between 10 and 90%. So the full range of the blue colors is a very likely range about this black line, which is essentially the median of these hundreds of simulations of changes in the ice sheet. And you can see that these are pretty big numbers. These are in meters. So the black line is about, you can see about 30 centimeters of a contribution to sea level from Antarctica when we incorporate these processes. But you can see that the top of the blue zone, which is within the band of realm of possibility, much, much higher levels, approaching, sort of flirting with a meter of additional sea level coming from Antarctica that we hadn't been thinking about before. But that's not very satisfactory, because you can see the range of the blue colors are anywhere between almost nothing happening in Antarctica, and Antarctica almost contributing a meter of future sea level rise. So the mission is to get that blue zone to be much tighter around the black line so that we have better confidence in the black line. So again, we use the geologic records and we use modern observations to tune the physics in the model to try to get that blue zone to get a little bit tighter. And you can see an example of adding different constraints on the ice sheet model based on different observations. And you can see that when we add these constraints, the dark blues are getting a little bit tighter around the black line. There's still a lot of uncertainty in the projections. That's important to appreciate. But we've been able to, in the last few years, reduce that uncertainty somewhat. Okay, 34 centimeters of sea level from Antarctica alone is the best guess in a high emission scenario. But when we go out beyond the year 2100, you can see what's happening. The black line is going to go right off the top of the screen. When we get to the year 2200, it's not 34 centimeters. It's more like 5 meters of sea level rise. It's in the beginning of the next century, about 100 years from now, that in a projection like this, it has now become so warm in the summer around Antarctica that the ice shelves are breaking up. The ice is starting to flow faster in these big Antarctic glaciers that are much bigger and wider than the ones on Greenland. And the ice actually starts to physically break up and contribute huge icebergs to the ocean. Okay, now, what has been exciting to me is that we're still representing these physics in a very simplistic way in the models that we make simulations at the ice sheet scale. And there have been different groups around the world now who are tackling this problem in very, very fine detail to try to understand the actual physics of the breaking, because that's really what is adding to these new projections of Antarctic generated sea level rise. It's the breaking, the physical fracturing of ice, the generation of icebergs. We really need to understand those physics. And there's been some really important work just in the last year actually supporting this notion that when the ice shelves are lost, there's this new mechanism that just the calving, the physical breaking of the ice, not just the flow, that we need to worry about. So this is becoming, you know, I think something that we really need to keep an eye on. The science is evolving very quickly here. Okay, and I actually think this is a demonstration of one of these very, very highly detailed models demonstrating that this idea that we had 10 years ago, that we needed to put these physics into a big continental ice sheet model, are real. Okay, so there's one model where we can see a big piece of the glacier breaking up off of its front because it has lost its buttressing. It's a very thick glacier, so the stresses in the ice are very high. And here's a completely independent modeling approach to the same notion. And you saw boom, 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 boom. Once you lose that resistance, there's no support, and the stresses within the ice are higher than the ice strength can resist, and it just physically breaks up. Okay, now what are the implications? The implications are that if we do not consider these processes, then we end up with very, very different perspective of what the future might hold in terms of sea level. So on the left is, again, it's this high emissions scenario of a future from a model that incorporates these processes, that fracturing of the ice in addition to the flow. And you can see now I've shown the plot out to the year 2300, and you can see the black line, the best estimate, is on the order of 10 meters of contribution to sea level rise just from Antarctica. This is just the Antarctic piece. It doesn't include Greenland and the other mechanisms. The little black line down here, that's what models show for the future without these processes. And the IPCC is still basing their projections of future sea level rise on models that mostly do not include these processes. So we have been working from a assessment perspective, like through the IPCC, in that kind of world. But what we're saying is if we look to the geologic past and we look to observations and we look to some of this new cutting edge modeling, then we need to be thinking about this as a possibility. Okay, now we've done our best. This is from a paper that was published in Nature just a few months ago. And now looking to see if we include these new processes, what are the implications for a world that we're able to keep below plus 1.5 warmer than today? So what we do is we follow an emission scenario based on the current NDCs, the nationally determined contributions. And when the global mean temperature reaches plus 1.5 degrees, we don't let the world get any warmer. And we run the ice sheet model and we see what it does. And the top plot, the red line, is the sea level rise that is being generated by Antarctica, going from the year 2000 throughout the century in one of these scenarios, a plus 1.5 world. And you can see that, okay, there's the sea level is sea level is rising due to Antarctic ice loss, but at a pace similar to Antarctica's contribution to sea level today. It's quite small, on the order of maybe less than 0.5 millimeters per year. There's a little bit of a kick toward the end of the century, but nothing dramatic is happening. The second panel shows what happens if we allow the world to warm to +2. And you can see that the red lines look similar, +1.5 and +2. There hasn't been any systematic step change in the Antarctic system. And the reason why is that it hasn't gotten warm enough in the summertime so that we start to get a lot of that meltwater on the surface of the ice shelves to help break them up. The bottom slide is what happens if all the nations that signed up at Paris actually follow their nationally determined contributions to the letter of the law. So we follow Paris policies as they exist today. We reach about plus 3 degrees warmer than today in the year 2100. And you can see in about 2060 to 2070, the red curve goes up, way up. So we've obviously crossed a tipping point in the system where it's gotten warm enough in the summer so that we're flooding some of these ice shelves with meltwater and they're breaking up, and these processes kick in. It's completely different. So remember, this is a model that has been calibrated and tested against making sure that it does a good job simulating the modern ice sheets. It's also been tested against being able to model past changes in the ice sheets. And this is right now what we're thinking is our best guess in terms of where the tipping point for something really bad and scary to happen in the Antarctic system. We don't want to go any more than +2, and it would be safer based on all the uncertainty, right? The big stretch in the blue curves, there's a lot of uncertainty in all of this, would be better off staying closer to +1.5. These are just some images to see like what's happening to the ice sheet and where most of the action is in that +3 degrees scenario. And it's within that blue box. You remember me talking about a piece of the Antarctic ice sheet that is sitting in a big, deep, bowl-shaped basin that's 2 kilometers below sea level? Well, this is the healthy ice sheet, the way it looks today. There's the year 2100, and we've started to lose what little is left of today's ice shelves in that stretch of the coastline. It's getting a little bit above freezing during the summer months. Those are 2 important glaciers, the Thwaites Glacier and the Pine Island Glacier in West Antarctica. This is West Antarctica, by the way. And remember, this is the part of the ice sheet that causes extra sea level rise in North America. Okay, so after the year 2100, the next century, you can see that a huge chunk of the ice sheet has been taken out. And we have contributed 154 centimeters in this particular simulation to sea level, okay, just from the Antarctic ice sheet. And so this, we add on to Greenland in thermal expansion. Okay, now I'm going to wrap up this section of the talk, and then we're going to just have an interesting conversation. Shana Sadai, one of our star graduate students at the University of Massachusetts, is going to say a few words about the climate justice implications of this that I think are really important and fascinating. So can we stop this once it starts, right? That's a fundamental question. The way to stop this glacier here, the Thwaites Glacier, from destroying the West Antarctic ice sheet, the way to do it would be to regrow those buttressing ice shelves. So if we can regrow and establish the ice shelves and they pin down on some bedrock, they'll start to provide some support, and they will let the ice sheet actually reestablish itself and sort of push its way back out into the ocean and regrow. But an ice shelf, because it's floating mostly in contact with the ocean, it can only regrow if the oceans get cool enough to allow it to regrow. And the ocean has a huge thermal capacity. It takes a really long time for the oceans to both warm up. That's a good thing because the oceans have been really saving us from a lot more warming than is happening because they're absorbing a lot of heat. They also take a long time to cool down. That's the flip side. So what we're going to do is we're going to follow an emissions trajectory following the NDCs. So we're on a +3 degrees C path. And then at some point in the future, we're going to just imagine, it's a little bit like science fiction. We're going to say the world has developed some technology that can actually suck CO2 out of the atmosphere, put it away someplace. And so we're going to have the CO2 rising. And then at some point in the future, we're going to start to pull it out of the atmosphere. And the CO2 will come back down again. And what we're going to do is we're going to see what happens if we delay developing that technology in the year 2030 or in the year 2040, in the year 2050, We'll wait to the year 2060 to turn on that technology, 2070 and so forth. And we'll see what happens to the ice sheet. Okay, the top plot on the left is what happens to the ice sheet. So this is sea level rise coming from Antarctica, going out to the year 2100. The black line at the bottom, that's if we just let the ice sheet respond to today's climate. There's no warming relative to the year 2021. Okay. The purple line is we allow some warming to the year 2030, and then we start to take CO2 out of the atmosphere. Then the next light blue line, we wait till the year 2040 before we start to suck CO2 out of the atmosphere, and so on. And you can see that there's a jump someplace, and it's between the yellow line and the red line. So once we wait until sometime later than roughly the year 2060 or 2070, even though in the year 2070, we're starting to really rapidly pull CO2 out of the atmosphere, the ice sheet doesn't care. These processes have kicked in. It's lost some of its ice shelves, and they are not regrowing because the oceans are too warm. And even if we wait in this bottom plot, which is the same set of simulations, but I'm just showing you what they look like if you go out for hundreds of years, you can see that the ice sheet doesn't recover. And in fact, the timing in terms of the choices that we're making today have a huge impact on the long-term evolution of the ice sheet. So, you know, in a world where the climate doesn't change relative to today, yes, Antarctica contributes, you know, a little more than a meter of sea level rise over hundreds of years. Perhaps we could cope with that. Our coastlines could, in many places, deal with that from an engineering perspective. But, and again, this is a plus 3 degrees C world. This is not, you know, a high emissions scenario. This is following the current NDCs. If we do nothing to develop technologies to suck CO2 out of the atmosphere, and we wait, there's a delay in mitigation, and we follow the black curve, you know, it's a much, much different scenario. So the point here is that we can't rely on these unproven technologies. And even if they are developed, they're not going to stop or slow down. They'll slow down things a little bit, but they're not going to stop something pretty serious from happening once they start in terms of ice loss from Antarctica. So it would be better, in my simplistic, naive thinking, to just keep the fossil fuel in the ground where it belongs and just not go there. Okay, I want you all just to think a little bit beyond the year 2100. It's really important that we have a longer term perspective. I'm looking at some of the youth out on the streets protesting as I walked in today, and right, some of them are going to be alive in the year 2100, and certainly their children are going to be facing the next century. So there's some good news here. Even though, you know, we've recognized that there might be processes that our community, the IPCC, maybe has been underappreciating that could drive really dramatic, potentially catastrophic rates of sea level rise in the future. If we're able to keep the temperatures in the future down into that sort of plus 1.5, plus 2 degrees, Paris Agreement sort of ideal world, things aren't so bad. We'll continue to feel sea level rise. We'll continue to have increasing impacts, but at a pace that we will hopefully be able to manage. Once we get to something like plus 3 degrees, it's a different story. And again, once these processes kick in, there's really no turning back. Okay, irreversible. If we go to an emission scenario, you know, like sort of a worst case, extreme sort of business as usual, sort of future world, we're talking about in the year 2200, would be measuring sea level rise and the rates of sea level rise in several centimeters per year, more than 5 centimeters per year. Okay, today, remember, we're at 4 millimeters per year, and it's causing havoc around the world. Imagine what 5 centimeters per year would look like. Okay, and if, you know, we think about going beyond the year 2200, the 2300 sort of perspective, we're talking, you know, remapping 10 meters of sea level just from the Antarctic piece. the Earth would look different from space. Everything you just saw assumes that Antarctica and the glaciers that have lost their ice shelves and are now breaking up and going out into the ocean, we're assuming that they could never behave any faster than the glaciers that we observe in Greenland. So we've actually put a speed limit on everything you just saw. So that's in Antarctica that has begun to behave like Greenland. But could the Greenland glacier, or the Antarctic glaciers rather, actually do something more dramatic than we're observing in Greenland today? And I personally think the answer is yes. And the reason why I say yes is that some of the glaciers in Antarctica are vastly larger in scale than the glaciers in Greenland that we're using to tune our Antarctic model. So the glaciers in the nice photos that I showed you of Greenland, where there's a lot of breaking up at the edges of those glaciers, the ice is very thick there, maybe 700 meters thick. It's a very thick glacier, but they're in relatively narrow fjords, 5 to 10 kilometers wide. And the size of those fjords actually provides some support for the glacier itself. And the fjords can get choked with chunks of ice that can actually provide a little bit of resistance. Some of the glaciers in Antarctica are twice as thick as those example glaciers in Greenland. And instead of 10 kilometers wide, the Thwaites Glacier that caused West Antarctica to break up, it's not 10 kilometers wide. It's 120 kilometers wide. And if it were to start to break up and retreat into the interior of West Antarctica, the ice that will be breaking and falling into the ocean, the ice will be more than 2 kilometers thick. So, the stresses will be enormous. And I would think much in exceedance of the strength of the ice, of the glacial ice. We just don't know how fast that kind of scenario could make sea level rise happen. Okay, now I'm going to end with this slide. This is from what just came out, the IPCC AR6. They did their best job to provide guidance. They're providing the world guidance as to what their best estimate of future sea level rise is. They are relying, again, largely on ice sheet models that don't include these processes that we just talked about, the covering of ice shelves with water, they break up, we lose the buttressing, and then they start to break. And down here in the bottom, you don't have to really focus in on the numbers. They show projections of the future for the different SSPs, the different emission scenarios. And they're down here on the bottom, run out to the year 2100. So this is all the contributors to sea level rise. It's Greenland, it's thermal expansion, it's mountain glaciers, it's Antarctica. And there's a range of uncertainty about their best guess, which is the solid lines. You can see that range of uncertainty. So this is their so-called likely range, 17th to the 83rd percentile range. And, this is noteworthy in that you can see that in the higher emissions scenarios, the likely range actually, in some situations, right, it's exceeding 1 meter. Okay, so this is the likely range. If we were to look at the very likely range, like the 5th to 95th percentile level, we would see that expand, maybe up to 2 meters or so. The IPCC really didn't know at the time what to do with these new processes. So they never incorporated them into the actual probabilistic projections. They're just a caveat in the AR6. They're the red dash line. So the red dash line is really just sort of a sketch as to maybe, Rob DeConto and his colleagues are correct, and that these brittle breaking processes are going to end up becoming an important player in the future of sea level rise. And remember, I showed you the vast difference of models that don't incorporate these processes in a future warming scenario versus the ones that do. And that's illustrated here. Here, the bar on the right is the same sort of graph, except now representing the world out to the year 2300. Again, the bar That's the likely range. And you can see there's a lot of uncertainty in future sea level, again, mainly because of the Antarctic component. But then there's these other processes represented by, well, maybe there's something much worse that we need to worry about. And I would argue that based on what I think is a conservative approach to this problem, is saying, let's just imagine that Antarctica starts to behave like Greenland, which we've observed. That would sort of be like this dashed red line. But there's a possibility that dashed red line actually is something even much higher. And so we really need resources. We need more modeling teams working on this. The community some of our community has really begun to galvanize around this problem. But, there's unsatisfactory uncertainty still in future sea level estimates. It's being driven by Antarctica. And I hope that I've convinced you that because the rates and the magnitudes of sea level rise that Antarctica can generate, once it gets warm enough so that we get that meltwater on those ice shelves, and that starts to happen above Paris Agreement sort of temperature aspirations, it's something we really need to keep an eye on. Okay, so I'm going to stop. I would like Shana, if she is available. Oh, great, fantastic. So I'm going to introduce Shana Sadai from the University of Massachusetts. She's going to say a few words about the climate justice implications for a future with a lot of sea level rise coming from Antarctica.
Thank you so much, Rob. So yes, as you can see, there is still a lot of uncertainty and there's a lot of risk inherent in the Antarctic ice sheet and in breach of instability points if the temperature gets too high. So Antarctica not just contributes to sea level rise, it also has implications for global climate. And so one of these that's particularly important with respect to the Paris Agreement is a negative feedback on the rise of global mean surface temperature. So a positive feedback is something that will speed up warming, and a negative feedback is something that'll slow it down. And so work that's been done to try to assess the climatic impacts of ice sheet loss has occurred over the last few decades. And as models get better and better, we get a better picture of what that might look like. And so one of the things that global climate models, they're excellent. They're state-of-the-art pieces of technology. They can teach us a lot about future predictions. But one thing that global climate models currently lack is dynamical ice sheets. And so in order to assess the climate implications of ice sheet loss, what we need to do is do what we call freshwater forcing experiments, essentially telling a global climate model what amount of meltwater a dynamical ice sheet model is expecting to happen. And so work that was done by Rob DeConto and Dave Pollard back in 2016, their paper on the long-term contribution to sea level rise gave some of these predictions of how much melt might occur. And I used those predictions to drive a global climate model to see what the impact on overall climate was. And one of the main things that came out of that paper is that there's a very strong negative feedback. This is occurring because of the growth of sea ice in the Southern Ocean around the continental margin of Antarctica. So as the ice sheet begins to melt, that ice sheet is made of fresh water and the ocean is made of salty water. So as the fresh water mixes into the salty water, it can change things about ocean circulation. And it can also make it easier for sea ice to form on the surface, which is a little bit counterintuitive because we're still running these under RCP 4.5, and this data is for RCP 8.5, a high emission scenario. So it's counterintuitive to think that in a warming world, we could still have a growth of sea ice. But that is one thing that's coming out of the global climate models. So as a result of the growth of sea ice, we have the albedo effect, which is where that sea ice is highly reflective. It's going to reflect back part of the incoming solar radiation. It's essentially the opposite, what the models are predicting, of what's happening in the Arctic. In the Arctic, we know there's a vast loss of sea ice, and so that darker ocean surface is exposed, which is absorbing more radiation, causing Arctic amplification and a high level of warming there. What this model of freshwater forcing experiments were showing was that with the growth of sea ice, you get enhanced reflection off of the surface of that sea ice, and that can delay global mean surface temperature. So these results were published in Science Advances last September by myself, Alan Condren, Robert DeConto, and David Pollard. And what we have here is the negative feedback, the amount of the delay of the global temperature rise, the difference that we had between when I run the global climate model using this freshwater forcing input to see what the effect is, and when I run it without that to see what the global climate model would say would happen without that ice sheet input going in. And so that red line is showing the negative feedback, and the blue line here is showing how that affects the ice sheet. Because of course, any change in the climatology is going to change the onset of when melt begins on the Antarctic ice sheet and when large-scale retreat is going to set in. And so what we found in the paper that Rob just described to you that was published in Nature in May of this year was that this delay in the air temperature rise delays the loss of the ice sheet for a little while. But that blue line is showing that even with it delayed, there is a very significant contribution to sea level rise, an extremely dangerous contribution. And so in light of the Paris Agreement being defined in terms of global mean surface temperature, for part of my dissertation, I've been assessing what are the climate justice implications when you have a negative feedback on global mean surface temperature rise in conjunction with a climate impact that's exacerbating risk like sea level rise. And so this paper I've been working on for the last 2 years. It's about to go into review tonight, actually. So you will have a preprint of it available soon. But one of the things, oh, sorry, that's cut off a little bit there. This is a plot showing Antarctic sea level rise regional variation. And so in assessing the climate justice implications, we've been looking at different forms of justice: procedural justice, recognition justice, and distributive justice. Effectively, for procedural, I was wondering, how did we come up with a temperature target? Because having a temperature target and then having these negative feedbacks with the climate justice implications, we assess the process of what happened leading up to that temperature target. What I'm going to speak to you about right now is the distributive component. So the variation in spatial and temporal impacts as a result of sea level rise. And so this plot, as Rob described earlier, as the Antarctic ice sheet gets lost, the spatial pattern of where that sea level rise is mostly felt is happening more in the northern hemisphere. And so here, the purple line, that is where global mean sea level rise values are occurring. Everything above that purple line is places that are experiencing higher than the global mean from the Antarctic contribution to sea level rise. And everything below is, of course, where that sea level is falling close to the ice sheet as a result of gravitational impacts. And so what we wanted to assess was how does this regional variation impact the Alliance of Small Island States? So the Alliance of Small Island States is a United Nations negotiating body. They have been incredibly strong advocates throughout the entire history of the UNFCCC. And they were instrumental in bringing to the forefront the needs of communities most impacted by sea level rise, and especially in pushing for the inclusion of that 1.5 degree Celsius target. And not saying that 2 degrees was good enough, saying that we really need 1.5, especially for most vulnerable places. And so in analyzing this, in looking at the sea level rise from the Antarctic contribution, we find that AOSIS states, the AOSIS member nations, they are impacted by 12 to 30% above the global mean at each of those locations. And many of these states, especially atoll nations like Marshall Islands, Tuvalu, and Kiribati, they are at very low elevation, sometimes maximum of 3 meters of elevation. So especially in the long term, that presents very, very important climate justice implications, especially for multi-generations, especially when we're looking out to the children and the children's children of where will not be affected by this. That sea level rise and that long-term commitment especially commits us to vast inequities in the future. And so I think this is really important to keep in mind. We often talk about 2100 as being the endpoint of policy negotiations, but we have got to think long term, especially when we're talking about a multi-centennial commitment to sea level rise and a multi-millennial commitment to elevated sea levels. We have got to keep that sea level rise as low as possible in order to protect those most vulnerable to sea level rise, coastal communities and island nations. And of course, these numbers, the physical changes caused in the Earth system by climate change, are always impacting at the local level in conjunction with sociopolitical variations in every place. So you have to look really at the regional and at the local scales and really talk to the people on the ground about what they need in terms of adaptation support and how best to mitigate to prevent the worst impacts. And so that's what we would like to say, that there are climate justice implications associated with all of these things, with all of the sea level rise. This is why we really care about this research, because we care about people and we care about ecosystems and we care about the planet. And so that's why it's so important that we keep fossil fuels in the ground, that we reduce emissions, and that countries have 1.5C compatible plans so that we can really do the best that we can here at COP26 and at all the COPs going forward. Thank you very much.
Thank you so much, Rob and Shona, for an absolutely fantastic pair of presentations. We have just a little bit of time for questions, so I'd like to invite both of you back onto the stage for a moment. And we'd really love to hear some questions from our cryosphere hubs in Stockholm and Geneva. So if any of you have any questions, do drop those in the chat. Do we have any? Okay, no. So in that case, I think we will go to questions from the floor. And I believe we have a couple of questions already. Would you like to come up and speak your question to the microphone?
Hi, thank you both. Can you hear? Okay, it sounds like nothing. Thank you for this. This was really, really interesting. My question is about AR6 and that dotted line. So it's unsatisfactory, but I wonder if you think it's an improvement over previous assessment reports that didn't even have any sort of exploration of that. So I was wondering if you could speak a little about, even though it's clearly not adequate to the work that you're doing or representative of the work that you're doing, how do you see it as an improvement if you do?
That was a great question. So the question was regarding whether or not we view the IPCC's inclusion, or at least trying to illustrate the implications of some of these other processes. I think it absolutely is a step in the right direction. And it is an advance relative to previous reports. I think we need to come up with some creative ways to incorporate these alternative outcomes within a single probability somehow, because policymakers are looking for more guidance than that dashed red line. I think a lot of people don't know what to make of it. At least I have been asked about this many times, like, what do we make of that dashed red line? What is the probability of that outcome? It's described in the IPCC text and on the figure as a low probability, but high impact storyline. And so, okay, what does low probability mean? This is a challenge, and I'm hopeful that as more work is done on this, and there are more modeling groups that are trying to represent these processes, we'll be able to, in the next IPCC, perhaps actually incorporate these processes into the projections. This slide that I didn't show before, it's just showing, so for example, it's a low emission scenario on the left, high emissions on the right. This is you can go to the summary for policymakers and find these numbers. I just plugged them into a table, and you can see the individual contributions to sea level rise in the year 2100 from Greenland, from glaciers, from thermal expansion. I'm missing a couple of numbers in the table. But the point is that these are the main AR6 projections without the processes when you add everything up. So what this is suggesting is in the year 2100, 12 centimeters would be the central estimate. And then this is the likely range coming from Antarctica. So this is the total. You can see that there's the numbers on the left in the low emission scenario don't really change much whether you include these processes or not. It's really for these higher emission scenarios where we're able to get the ice sheet to be warm enough where they kick in. So low emissions, really, it might end up being somewhat moot because these things don't really kick in and they don't become widespread. But in the higher emission scenarios, they're quite impactful on the scenarios. So here's an example. 1.35 meters. In my rush early this morning, the table got a little bit messed up. So these are the numbers, I think, for the year 2100 here. They're not the rate of sea level rise. Everything looks like it got shifted down. But you see that estimate of 1.35 meters. IPCC AR6, the main projections. Now with these processes, it's something much higher. So, you know, I think that most of the community are still operating in this sort of space, but I really think we need to just keep it in the back of our minds that this could be a future possibility. And we can not go there if we are able to keep the global mean temperatures down. It's really that simple.
Okay, so I think, do we have time for one more very quick question? Yeah, so if we could, I think, we have one more question from the floor. So if you could try and state your question and your answers fairly briefly, just so we can move on to the next event, that would be fantastic. Thank you.
Take that off. I just had a question. I'm not a scientist, so I don't get it at all. But so you talked about this scenario that we had to capture and store carbon before 2060, and I'm always a bit skeptic, and I don't know much about these technologies. Is it actually doable? Do we have these technologies, and if we capture that carbon, where do we put it exactly? Yeah, thanks. That's just that.
I mean, you could. I mean, neither of us work on clear air carbon capture, which is what these scenarios are assuming. And those technologies have been shown to be viable theoretically, and they just haven't been built to scale yet. And so I think it's unproven as to whether or not we'll, in this sort of time frame, be able to develop those technologies at the scale that would be needed. And you saw that just following the NDCs, like what we're on path for now, assuming that we actually follow the NDCs, okay, even following the NDCs, even if we were to develop those technologies in the later part of the century, it would probably be too late, because once these processes kick in Antarctica, they're hard to stop.
Yeah, and I'll just add to that I think I don't think we should rely on those technologies getting ready. I think it's much more dangerous to rely on that and have it not pan out or have it come with additional negative side effects than it is to just reduce emissions now, and just really focus on shifting away from fossil fuels, reducing emissions from animal agriculture and other sources, and just really not relying too much on unproven technologies to save us.
Yeah, Shane is right. I mean, the technologies to reduce emissions now, they're here. And we know they work and we know they can scale. Makes sense to me.
Fantastic, thank you. And we do actually have a little bit more time for a few more questions. So there's still time, Geneva and Stockholm, if you'd like to drop some questions into the chat. But otherwise, please give me a little wave if somebody from the floor has a question they'd like to ask. Otherwise, I think I might take the opportunity then to ask you a question. So you've talked about these really sort of obviously very large scale impacts, and you've also talked about the climate justice implications. And I guess I just wanted to ask a bit about, while we're here in this context at COP, what do you think this really means? Obviously, there's the added urgency of mitigation, but I guess what are your thoughts about what this means for kind of balancing the need for mitigation and adaptation, and possibly also loss and damage? And just thinking, even a small proportion of some of these really large scale changes you've talked about is still a very substantial impact. So I just wondered if you could talk a little bit more about what you would like to see at COP in recognition of that full spectrum.
Yes. Yes. So both of those things are particularly important. Currently, I think that the liability for loss and damage, the mechanisms for liability, especially for industrial producers and historic high emitters, they're not quite adequate. And the adaptation financing as well. The adaptation financing is particularly important, and that's really needed now. And there's supposed to be $100 billion in aid coming, but that aid has not materialized in the time that it should have, and that aid has been often in the form of loans instead of grants. So there's also, we need to be thinking about the way the adaptation financing is working with debt. And so we really need grants instead of loans, so that people countries on the receiving end of these of this adaptation financing are not being put into debt because of it. And there's also it's really important that that adaptation aid is spread in a way that is equitable. Currently, small island states are only getting about 3% of that aid, and often in the form of loans. And so that was from a new Oxfam report that was just released, I think, a couple months ago, that was talked about at the Virtual Island Summit. So yes, loss and damage and adaptation financing are extremely important components of addressing sea level rise, as well as, of course, mitigation to prevent it, so that this does not play out in the more severe scenarios that we've talked about today to begin with.
No worries, thank you. Does anybody else have any more questions, responses or thoughts? Okay, so just one more question for me. I was wondering as well if you could talk a little bit more. I was thinking about those graphs you showed with the blue lines, and talking about I guess it's a question about communication. So as scientists, as you obviously went into, we don't talk so much about the implications of really rapidly evolving science, and the potential for us to be kind of focusing a little bit too much, perhaps on the lower end of what might be the case. And so obviously you've talked a little bit about the IPCC, but maybe for all of us here as scientists, could you say a little bit more about what you think we should be doing differently to communicate that, and perhaps a little bit more accurately?
Yeah, I think, as scientists, we tend to be conservative, and, for the sake of not losing too much sleep, wanting to err, if we're going to err, on the conservative side. And certainly there's a tradition in the IPCC style of assessment literature to do that. So, the question is to how to better communicate the uncertainty, the possibilities. I think we're beginning to get there. I mean, there are people like me who are beating the drum that there could be some outcomes that fall way outside the likely range. And that's not pulled out of thin air. Remember, for example, a model that is being used by the IPCC in their main core projections down here can't replicate Andrea's last interglacial or other geologic past scenarios. So there, I think, more of us, I'm inspiring the students and the postdocs that I work with to get involved in this sort of activity where we can be out here face to face with people. I think building trust is a big part of this in terms of science communication, maybe the biggest. And that takes just getting out and meeting people and making yourself accessible to the general public and to going out of your way to come to events like this. It's a challenge. It's a balancing act because it takes away, in some ways, from the time that we have to be. I could be at home, working away on the computer and trying to improve the models. So that's an interesting, issue too. But I think this balance of the people doing the work, publishing the papers, interfacing with all of you, just like this, is really, really important and key.
Yeah, and I'll just add, it needs to be a collaboration between scientists, between policymakers, and we need to bring in frontline communities. We need to be listening to what people on the ground are experiencing and what their needs are. So at all levels. And yes, this is a perfect forum for that because there's a lot of people and a lot of groups represented here. Thank you so much.
Thank you so much. We're going to take a very short break, just a 5-minute break. And then our next event will be looking in a little bit more detail at the importance of ice shelves, and that will be with Scripps and with NSIDC. So please do feel free to have a wander around or stay for the next event. And thank you again so much for coming.